So today I'm going to talk about one of our recent works done by my PhD students, Ankit and Rahul, mainly by this guy, Rahul. So recently there was a talk on this active matter physics. There were beautiful slides. Let me show you a few videos from my side. So there is, what you see here is like bacteria, which is in the order of a few micrometers. So the bacteria, it's not only translating, but it's also rotating on its own on a two-dimensional surface. And there are several bacteria, they kind of collectively move together. They interact with each other hydrodynamically. They form nice, beautiful patterns. And the same thing you can observe even at higher length scales, out of centimeters, like you see these birds. Okay, you see these birds. They in the same thing, like they kind of interact with each other. They form these nice, beautiful patterns. And these are the living things, but the similar things we can also kind of prepare. We can prepare the synthetic active systems. Here we can see a bunch of colloids moving together. They're interacting hydrodynamically. And here we see a slightly higher version, is like in the order of maybe a centimeter or so. Okay, these synthetic active particles, they're kind of translating, rotating in a free, but here in this case it's not free space, but there's a boundary. Okay, and what you can see is these curved boundaries, and then this active particle, these synthetic particles, they tend to move close to the wall. Okay, and they form these nice circular patterns here. Here, the important thing that is that we have to note down is like how these boundaries are affecting the transport behavior of active particles. So as a motivation, of course, we are not biologists. As a motivation, we look at this airways where these tubes, they just oscillate as a function of time. So they pump the fluids and particles along this long airways. There's like long tubes, and similar things we can also observe in ion channels, where these ion channels they regulate in the sense like they change its shape over a period of time. So by keeping these two things in mind, we ask a very simple question, like how these active particles diffuse in a confined geometry, where the confined geometry is not static, rather this confined geometry is oscillating. It means the shape is changing over a period of time. So as a model system, we consider along a tube, we fill with active Brownian particles. As you know, these active Brownian particles, they can move on their own, they can rotate on their own. That's how we can differentiate between a passive particle and active particle, right? Where this a passive particle cannot rotate, they can move, they can have only translation diffusion coefficient, but here, this active Brownian particle, they can have both the translation as well as the rotation diffusion constant. So we can write down these Langevin equations in the O-damp limit. We can neglect the initial term, and this is the self-propelled, V0 is the self-propelled velocity, and this is the translation diffusion coefficient. And the second equation will take care of the rotation degrees of freedom. Here, this eta and zeta, these two are the Gaussian white noises. And here, the tube can be modeled a simple sinusoidal function, something like A sine 2 pi by L z minus omega t plus b, where omega is the frequency of this oscillation, L is the periodicity of the tube, where A and B will control the area of the tube, means the maximum area and the area at the bottleneck. Okay, so here the condition is B should be greater than A. Otherwise, we don't get any opening here. In other case, when A equals to B, this bottleneck width closes. That means you get a single cell. So when we have these Langevin equations, we can just write down a simple code. We can calculate the mean velocity and effective diffusion coefficient in the long-term limit. And just for simplicity, we make these equations dimensionless by using the periodicity L and a characteristic timescale tau, which is defined as L square over dt. Now the question is, can we solve this problem analytically? So, numerically is fine. We have equations, we can write down simple equations, it is very simple stuff. But the thing is, how can we understand this problem analytically? So if you want to solve this problem analytically, we need to, the first point that the first step is write down a focal Planck equation in 3 dimensions. By taking both, not only the position dependent, like not only this x, y, z, but also we have to take this orientation into account. So this is the focal Planck equation 3D, in 3 dimensions. So this dr and this v0, these two terms will take care of the activity of the terms. This is the translation moment, this is the rotational moment. And if you, of course, if you throw away these two terms, you'll go back to this Fokker-Planck equation for a passive particle. The question is, what is the difficulty in solving this equation? The difficulty is the particles are moving in a confined geometry, right? The particles cannot escape. So whenever, if you want to solve these equations, we need to apply the boundary condition. That means the flux across the boundary is 0. So the boundary conditions are the difficult part here, right? So applying boundary conditions and simultaneously solving this three-dimensional Fokker-Planck equation is a difficult task. So what we can do is, we can make some assumptions and bring this three-dimensional system to an effective one-dimensional system. By the way, we are looking at the tubes of small width. So it basically is one-dimensional, quasi-one-dimensional tubes, right? So the width is very, very small compared to the periodicity of the channel. So we can assume that particles take less time to equilibrate along the transversal direction compared to the longitudinal direction. That means, I mean, we can assume that there is equilibration along the transversal direction. So that, in other words, the transversal components, let's say X and Y, they are fast components compared to the longitudinal component, which is Z, right? And not only that, we also make an assumption that this the tube is varying smoothly. Okay, it's not a rough channel; it's a very smooth channel. So when we make these two simple assumptions, we can bring this three-dimensional system, three-dimensional equation to an effective one-dimensional equation, which is called Fick-Jacobs approximation. Right. So here, what we did was we have eliminated the X component and the Y component, the transversal components, and we have only the Z component, which is along the length of the channel of the tube. Right. But while doing that, we had to pay the cost. We'll get a free energy, which is, of course, in this case, is like the free energy. Basically, in this case, it contains only the entropy contribution because there is no force acting on the particle. So how come we get this entropy here? This entropy is coming because of this geometrical confinement, because you're confining the particles within the channel geometry. So when you bring this three-dimensional system to an effective one-dimensional system, the geometrical contribution that appears in this entropic term. So here H of T is nothing but the cross-sectional area of this tube in 3 dimensions. In 2 dimensions, it just is a width. So not only that, in here we have this dt, translation diffusion constant, which is a number, this kBt by gamma t, whereas here, when you bring this 3D to an effective 1D system, we have to introduce this position-dependent coefficient. That means the diffusion is not same everywhere. For example, in this case, the diffusion has, the particle has a lot of space to diffuse along the transversal direction at this location, whereas here, the space is less. So the available space for a particle is not same everywhere. So that is taken into account by introducing a position-dependent diffusion constant, dz of t. So this is our, I'm not there yet. Sorry, I'll be quick. So this is the equation. Now, okay, we can solve these equations. We can read out the current, and then from the current, using the current, you can calculate the mean velocity, and from the moments, because we can solve these equations to find out the steady-state probability distributions. From this, you can calculate the first moment and second moment, and this will give you the diffusion, effective diffusion, and this J will give you the mean velocity. So analytically, we can solve these equations, and this is just a probability distribution. Numerically, we have solved this problem, and then we calculate the probability distribution in 2 different directions, like along the Z direction and along one of the transversal direction, that is X. So here you can see that the probability distribution along the transversal direction is more or less flat, which was our assumption. So, by the way, this is in the adiabatic limit. That means the frequency omega is very small. So in the adiabatic limit, the assumption that we made was, it works well. And of course, this is the probability distribution along the Z direction. Now, if you look at the mean velocity and effective diffusion as a function of omega, omega is the frequency of these oscillations. What you see is, as you increase omega, the velocity increases linearly, right? They increase linearly, but at high frequencies, what happens is, particles the channel is modulating at very high frequencies, so particles do not feel these boundaries anymore. It will feel only the small opening, which is the bottleneck, which is something like a small narrow pipe, right? That's what particles see. The particle won't see the entire space because this shape is oscillating rapidly. So in the flat case, of course, something like active particle is moving in a flat channel. So that is 0 because the mean velocity is 0. Particle can move either forward direction or backward direction. So the net movement is 0. So the velocity is 0. So there is an increase and there's a decrease. So obviously there is a maximum. which is something like resonance-like behavior. That means at optimal frequency omega, we can have a higher velocity particle can have higher velocity, and this is the corresponding effective diffusion. So yeah, so this increases, and then of course this is again like flat channels. So this we can find out by this effective diffusion in the flat channel can be calculated. I mean, this is a known formula for active particles. This is available in the literature. So here what we're doing is like we are varying this channel, one of the channel parameters, that is A. So as you change A, that means as you change the shape of the channel, in the flat channel case, velocity should be 0. But as you change the shape of the channel, that means as you increase the width at the maximum, but at the same time you're decreasing the width at the bottleneck. So in this situation, what happens is the velocity is 0 initially, but then velocity increases linearly. But when it closes, that means when A goes to B, it is something like in a single cell. In other words, a complete wave packet is translating. So that is something that you can calculate directly. These are textbook stuff. So this like phase velocity, which is omega L by 2 pi. So the velocity matches with this velocity, with this phase velocity. So that's it. So we can we can introduce this. We can make the simple assumptions. We can bring this 3D system to an effective one-dimensional system, the Fick-Jacobs equation, to calculate the transfer properties of active Brownian particles, and we observe a resonance-like phenomena for this particle current. And for more details, please see this poster. Thank you.
We want very quick question.
Maximization of the velocity at specific frequency?
It is something like resonance frequency, because the tube is varying with some frequency, and there is another time scale associated with the active Brownian particle. So when these two time scales match, there will be a maximum. It's something similar to the stochastic resonance that we studied.
Actually, you said that a low channel frequency as well as high channel frequency, it's non-diffusive. So
0.
Yeah.
Almost velocity 0 and diffusion is like almost constant. Yes.
Is there any critical frequency that you find it like where the particle starts diffusing and shows that behavior?
It is there. Maybe it takes little. Maybe I can explain to you during the coffee time, because it takes some time to explain. Okay. Yeah. I have to show some videos. Okay.
Let's thank the speaker again.